let's consider how we add one lottery to another lottery, what that looks like in terms of the notation, and get into this idea that a risk-averse person will never want to take a coin flip risk. They'll never want to add they'll never want to take on a fair gamble and sort of show that in a formal way. Okay, this is problem 7 from Osborne and Rubinstein's preferences under uncertainty. Okay, so the problem says additional lottery. An individual faces the monetary lottery P. Okay, so let's depict lottery P first. By the way, if you read in this section, they've asked us to assume expected utility model, expected utility preferences, monetary prizes, and risk aversion. A risk-averse individual whose preferences are consistent with expected utility, and we're using the V to denote the Bernoulli function, the expected value, whose expected value represents the individual's preferences over any possible lottery over the outcomes. V we can think of as the utility for a particular outcome, and we assume that V has a derivative, it's differentiable. Okay, additional lottery. Individual faces the monetary lottery, lowercase p, has some probability of each prize, if we recall. These prizes are monetary, as just said. Okay, so what does that look like? Well, that's going to look like something like, using the notation, it's going to look like some probability, P with probability 1, you'll have prize 1, and then, that's again, this means, and with some other probability, you'll have probability 2, you'll have prize 2, etc. up to, well, usually we think of we often use K to index the last of the prizes. So with probability capital K, we have prize ZK. This is 2, not K. Okay, so we call this lottery P. The expected value, okay, so now it says he has made the following offer. He's facing this lottery already. This is the risks he faces through the course of her life to begin with. She's facing investments. There's disasters that can happen. ... He has made the following offer. For each realization of the lottery, another lottery will be executed, according to which he will win an additional $1 with probability 1/2 and lose $1 with probability 1/2. Okay, in other words, they're saying you face these risks. Do you want to also take on a 50-50 risk of winning or losing $1? Now we know that basically our definition of someone who's risk averse is that they would reject all fair gambles and all monetarily fair gambles, and a 50% half probability of winning $1 and a half probability of losing $1. The expected monetary value is obviously 0. So we know they should reject that, but we need to show that using our assumptions, using our model of expected utility, assuming they're risk averse, they have this concave utility, etc. Or this concave utility function, etc. Okay, so first we're asked to describe the lottery Q he would face if he accepted this 50-50 lottery offer. So what would it look like, okay? In every state, so first of all, let's think, what is this coin flip risk? How do we denote this coin flip risk? Let's call the coin flip risk, I don't know, C. It's a half probability, not that, of gaining 1 and a half probability of losing $1. Okay? So in other words, what I need to do is to basically add this to every outcome. Every outcome I face, I also will have a half probability of gaining or losing $1. Okay, so I wouldn't just say I can't just do the and some half probability of this because I've already exhausted all of these probabilities should all add up to 1 already. So what I need to do is basically, add this to each of the possible outcomes. Another way of thinking of it is half the times, in other words, add this to each of these two. So half the time, if I accept this, I will gain $1 and also face all of these risks. And then half the time, I will lose $1 and also face all of these risks. Okay, so for instance, half the time I will gain $1 and then with probability 1, gain or lose whatever Z1 represents. So how do we depict this? Well, let's call this new lottery Q. Every Z1 or every Z, so lowercase k, should be split into within every probability we have half of that probability of getting a heads and also gaining 1, and half a probability of tails and also gaining 2. Okay, so in other words, in each of these cases, I also have lottery C. So in that sense, it's a compound lottery. So I have probability 1 of Z1. I forgot how we notate the second lottery. Let's say probability 1 of Z1 and lottery C, plus probability 2 of Z2 and lottery C. All right, but lottery C itself has probabilities in it, so we need to break this up. Or I didn't have to cross it out; it wasn't wrong. What does this lead to? Okay, for lottery Q, again for k equals 1 to k for all possible outcomes here, it yields the prize ZK plus 1. So the probability that I'm in this particular that this outcome occurs with respect to this initial lottery or gambles I face is P1. So with probability P1, I get ZK, with probability PK, so with probability PK, let's stay in this in general, I get ZK and lottery C, which means with probability K, I get ZK and with probability PK, I get ZK and one half probability of plus 1 and 1/2 probability of minus 1. Okay? So then I can say, well, what is the probability of any particular outcome here? Well, the probability of getting ZK, the probability of getting ZK plus 1 is PK times ZK, it's PK times 1/2 ZK plus 1. Okay, so we say PK times 1/2 probability of ZK plus 1 and PK times 1/2 probability of getting ZK minus 1. Right, where I get ZK as the outcome from the P lottery, but then I also lose the coin flip. Okay, so that's for any particular, one of these outcomes. But okay, so how do we state that overall? I guess I would state that as Q is. I could write it as this sequence of numbers. I write this as Q is 1/2 times P1 Z1 plus 1. So this 1/2 P1 has the dot operator times Z1 plus 1, but then also 1/2 P1 Z1 minus 1. And then also, and then I need to specify the next element just so you can see the pattern here. There's probably a simpler way of writing this. 1/2 P2 Z2 minus 1, plus 1, and 1/2 P2 Z2 minus 1, and then we put dot, 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 because we begin to see the pattern, all the way up to the K element, where we'll have 1/2 P big K ZK plus 1 and 1/2 PK ZK minus 1. Okay, as I said, there's probably a more concise way of writing this, but you get it. Okay, so now, we were asked to describe the lottery queue that he faces. We described it in words, and I've given you a way to notate it, maybe not the most efficient way. Okay, the next part of the question asks us to show that if he's strictly risk averse, he would reject the offer. In other words, if he starts with P, he would reject adding lottery C to it. In other words, if he's strictly risk averse, he must prefer P to Q, which I've illustrated here with this dot, dot, dot notation. Okay, so how do we do this? Well, we've stated that it's an expected utility maximizer, so we need to compare the expected utility of this lottery and this lottery. We need to compare this additive sum to this additive sum. Not this additive sum to this additive sum, sorry. We need to compare what you get when you replace these terms with the value function for each of these. So it's not just the expected numeric value that's important. You replace these with V of Z1, multiply those by probability, and then you add these with actual plus signs. Okay, so in other words, what we want to see is expected utility of P greater than, we want to show that it's greater than the expected utility of Q, where expected utility is as we have defined it, right? Summing over all possible outcomes. Here we're using index K is 1 to K. The probability of outcome K, here monetary payment ZK, multiplied by how much the individual values that particular monetary payment. Right, this is the expected utility of P because I said P of ZK rather than Q of ZK. Okay, we want to show that this is greater than. So this is under the what we're wanting to show category. Okay, we want to show that this is even strictly greater than, I would say. At least if it's strictly risk averse, strictly concave value of income function, we want to show that this is strictly greater than the equivalent for the Q function. Now, what is the equivalent for the Q function? Well, I can write this as a sum, and I've helped myself by putting in this notation. So I can write this as, and in fact, I can see that this 1/2 P1 term is going to be the same on either of these. But let me show you what I mean. Okay, so this is expected utility of P is equal to this sum, and this is an expected utility of the lottery Q is equal to the following sum. Sum over all K equals 1 dot dot K. So basically take the generic element. So we have 1/2 P1 times, and now remember we need to plug in the Bernoulli utility, the value of this. So we have V of Z1 plus 1, right? Because half the time I not only get Z1, I also win the coin toss. And now we just use a regular plus sign because we've already applied the value function. Plus, and a 1/2 sorry, I say this is indexed over k. So rather than P1, so it's P1 plus P2 plus P3, you know, the one version for P, for the 1, for 2, for the 3. Rather than putting 1 here, I'll just put K here. So it's going to go for first for 1 and then for 2 all the way up to however many elements there are, which is big K. Okay, so 1/2 probability of 1/2 times PK of getting what we originally were going to get, plus we win the coin toss, and then another 1/2 times PK, because here when we lose the, when we're in sort of state PK, but we lose the coin toss, we get V ZK minus 1, and that's it. That's the expected utility. Okay, but you know, I can simplify this a little bit because this is just a sum, so I can easily take out the 1/2 PK here. So this is equal to the same sum over K equals 1 dot dot K, 1/2 PK V. Now this term, you know, I just took out the 1/2 PKs, but we still have the V, two different terms here. V of ZK plus 1 plus V of ZK minus 1. Okay, but so do we know that, how can I know that this is greater than this? Well, they're both sums of k terms. And if every term, if each and every, this is a sufficient condition, right? If each and every term in this sum is greater than each and every term in this sum, then certainly the sum of those will be greater than the sum of the terms here. One thing to note, by the way, I swapped PK, I realized, for P of ZK. Okay, I use those I basically am using those interchangeably. So yeah, sorry about that. Because here, at one point I said P of Z, here I say P of ZK, but I actually was calling that PK. Okay, so the question is, and so let me switch it here also to PK just to make it more corresponding, where PK is simply the probability in lottery P that you get monetary outcome ZK. So this is PK. Okay, so what I need to show, or what I claim would be sufficient to show, is that each element here, PKV of ZK, exceeds each element here, 1/2 PK V of ZK plus 1 plus V of ZK minus 1. Okay, that's just going to come from risk aversion. Okay, from risk aversion, this is concave. This function is concave. And we know, I mean, we could prove this, but we know in general that for a concave function, it's easy to see in the case of a single variable. Let me make it sort of more concave so you can see it. If I compare a particular outcome to half of the outcome a little bit 1 unit above it and half of the outcome 1 unit below it, in other words, I compare it to the point on the line connecting these 2 points, this point will be below. Okay, an outcome is preferred to half of the outcome slightly below, with half of the outcome of, let's say, income $1 below it, and half of the outcome of income just $1 above it. Okay, this is just a property of concavity of a function. You know, the half the value, the increase, because the increase in this direction, because of concavity, because the second derivative is negative, because of that concavity, the increase in this direction is not as large in magnitude as the decrease as I move the argument in this direction, because we see the slope gets shallower everywhere. So it's steeper here than here. Okay. Now, so just to finish this off, to state it formally, we know that V of ZK, whenever V is a concave function, it's always going to be the case, at least for some small epsilon, and let's assume $1 is a small epsilon. Actually, let's forget about whether it's small or not. Okay, that might be true in general. I have to think about it. It's always going to be the case that this is going to be greater than half v zk plus 1 plus half v zk minus 1. Okay? Therefore, we know that all of these arguments are smaller than all of these arguments. Therefore, the sum of all of these arguments must exceed the sum of all of these arguments. So someone who is strictly risk averse would gets strictly higher expected utility from P than from Q, so they would reject the offer to take a coin flip risk on top of all of the risks that they're already facing.